Alright, so now let's go to the next problem, and that's problem 3. This has 2 parts. This one states, show that tan of 1 divided by 2x of 1/2 x equals to cotangent, or cot 1 divided by 2x minus 2 times cotangent of x. And then part B says, find the sum of the series, and series here, summation from n equals 1 to infinity of 1 over 2 to the power of n times tan of x divided by 2n. Alright, so now let's look at the solution to part A. So basically this trig identity we're going to try to prove. So first, recall the trigonometric identity from our earlier video. Went over proof of this one. So we have this one, tan x plus y, and tan x minus y equals to, right over here, tan x plus tan y, and then divided by 1 minus tan xy. The other one is going to be plus. You just switch the signs for this one. But in this case, what we're going to use is the plus, the plus version. So using x equals y equals theta in the tan x plus y identity, we get, and yeah, because you notice here's a tan 1/2 x, and what we're going to do is just write it down like this. You basically combine, we're going to combine the angles, because here this just has an x, doesn't have a y. So it has both there, and we'll call it theta for now. Yeah, so thus tan of theta plus theta is equal to, and just combine that there, it's going to be tan theta plus tan theta, then divided by 1 minus tan theta, times it by tan theta. Alright, so now what this equals to, let's just simplify this. This becomes, well, 2, just add the like terms, 2 tan theta, divided by 1 minus, and now this is going to be just squared, tan squared theta. And put this down here. Now this tan theta plus theta, that's just equals to tan 2 theta. And also recall that this just equals to, well, 1 over cotangent of 2 theta. So yeah, just recall tan, yeah, cotangent is just the reciprocal of tan, which is just basically 1 over tan theta by definition. Yeah, so cotangent is just the 1 over tangent. So then this equals to right here, 2 tan theta, 1 minus tan squared theta. And then what we'll do is we're going to move this over to this side, and yeah, just move this over to this, and move this other one over to the other side. So just cross multiply across. And what we're going to get is a setup like this. Yeah, we'll get a setup of cotangent 2 theta, that's on the other side, and I'm also going to divide this out as well. So divide this out as well, so we're just going to be left with a 2 there. This equals 2, 1 minus tan squared theta, that's because this whole thing moved over to the other side. And then we're going to be dividing also by tan there. Basically just flip it upside down, but keep the 2. But keep this 2 there. And then divide this by tan theta. So this equals 2, and you could also just simplify this. This equals to 1 over tan theta minus, and then tan squares cancel. Well, it just is going to be tan theta like that. Alright, so what this equals to now is, well, this just equals to, and this 1 over tan theta, that's just going to be equal to cotangent theta, then minus tan theta. Like that, and this equals to 2 cotangent theta. 2 cotangent 2 theta. And notice that our identity is, we're looking for tan in the form of cotangent. So what we can do is just move this over to the other side. Move this over, and then move this back. So what we're going to get is tan theta. And so tan theta equals 2 cotangent theta minus 2 cotangent theta. 2 cotangent 2 theta, like that. And now what we'll do is, well, we're just going to replace, so replacing theta with 1/2 2x, we will get our identity. So we're going to get tan 1/2 x equals to cotangent 1/2 x minus 2 times cotangent, and there's a 2 1/2 x, that's just going to be x, like that. And this is our answer. We could just double check. So tan 1/2 x, and then cotangent 1/2 x, and then minus 2 cotangent x. So it doesn't have a 1/2 there, but it's a 2 there. And that's exactly what we have right here. So that's a check mark there. Alright, now that we have part A, let's look at the solution to part B. So we need to find the sum of the following series. So this one right here, summation from n equals 1 to infinity of 1 over 2n x, and then tan of x over 2n. So let's just write that down for completeness. So n equals 1 of, this is going to be 1 over 2n of tan x over 2n. So notice this is x over 2n, but our identity is 1 over 2 to the power of x. So we want to write this identity such that we'll have a x over 2n. And we could do that by replacing x with this x over 2n minus 1. So using part A, but replacing x with x divided by 2 to the power of n minus 1, we have, and we could see that, let's just write this, tan. So instead of 1 over 2x, we'll have 1 over 2 times it by where x is right here, x over 2n minus 1. And remember, this is 1 over 2 is power of, it's the same thing as 1 over 2 to the power of 1 there, and this will cancel with this right here. I'll just erase that. So those cancel. So then this right here is equal to, well, 1 over, this just equals to x over 2n. Because you could just combine that power. So that's why we write x as, replace it with x over 2 to the power of n minus 1. So now this equals 2, and then cotangent, yeah, and this is going to be cotangent of the same thing, 1 over 2 times x over 2n minus 1, because you see the identity is the same thing. The next one, there's no 1 over 2. So minus 2 cotangent of x over 2 to the n minus 1. And yeah, so this one right here, this just equals to x over 2n. Yeah, so let's just write that out. So what we have is right here, this is tan of x over 2n equals to cotangent of x over 2n minus 2 cotangent of x over 2n minus 1. Alright, so now that we have this, so now let's take a look at the nth partial sum of the series, and that is right over here. So let's look at the nth partial sum. So we just sum it up to n instead of up to infinity, and then later what we'll do is apply this identity to every single every single term. So let's just write this down. So the nth partial sum is going to be written as Sn, and we'll write this as summation, and we'll change a variable. So it's up to n instead of infinity, and instead of n, we'll start with I equals 1, like that. 1 over 2 to the power of I, and then we'll have tan x 2 to the I. Now this equals 2, this equals 2 tan. When you plug in I is 0, I is 1. We're just going to get x over 2 to the 1, so that's just over 2, and then I'll divide this all by 2. The next one's going to be tan of x squared over 2. Actually, not x squared, x over 2 to the 4, or 2 to the power of 2. And then this is divided by, and this is 2 to the power of 2, that's going to be 4, like that. Yeah, so in other words, this is 2 to the power of 2. The next one's going to be plus tan, and then x over 8 to the power of 3, over, and then this can be 8. And this is again 2 to the 3. And here I quickly just moved it down over to here, and then just so we can get the next one, so we're going to go plus plus tan of x over 2 to the n. Over, this is going to be n, like that. 2 to the n, yeah, this is going to be 2 to the power of n, like that. So when I is equal to n, all the way up to there. So that is our nth partial sum. Alright, and now what we could do is apply the identity to each of the tan functions over there. So for example, for this one right here, tan x over 2, we're going to replace that over with this. So tan x over 2, yeah, this is just same thing as x divided by 2 to the power of 1. So this equals to cotangent, it's going to be x over 2, then minus 2 cotangent of x, because you have x over 2, and then this is going to be times by, yeah, this is you don't have that 2 there, so 2 to the power of n minus 1 there. And this x, yeah, so this is the same thing as writing x over 2 to the power of 1 minus 1, so that n minus 1, or, yeah, then that just goes to 0. Equals x over 2 to the 0, which equals to x over 1, which equals x. So that is that part. The next one here, just to illustrate it before we put it all together, tan x over 4, this equals to cotangent of x over, x over 4 minus 2 cotangent x over 3. I mean x to the 2, not 3, x to the 2 power of 1 there. Because you subtract 1. This is 2 to the 2. 2 to the 2, this is 2 to the 1. So basically each time you have 1 less. It's 2 to the n is a 2 to the n minus 1 there. And then lastly, in this one here, just tan x to the 8, just so you understand the pattern. So tan x to the 8, this equals to cotangent x over 8. Again, this is 2 to the 3. Minus 2 cotangent x over 4. This is 2 to the 2. Like that. Alright, so now we have all that, and let's put it all together. Let's put a line here. Thus what we have is the partial sum Sn. The nth partial sum is equal to, and we're going to replace this tan x over 2 with this, but then we also divide by 2. So that means this will have it as, put a bracket like this. It's going to be equal to cotangent x over 2. That's this part. And then divide by 2, minus, this one, the 2's cancel. So this is going to be minus cotangent of x, like that. And then the next one is, we're going to add a plus. Yeah, and we're going to divide this out right here. So tan x over 4 divided by 4 now. So we're going to go over to this side and look at, and then we're going to add that here, but divide by 4. So this is going to equal to plus cotangent x over 4, divide this by 4. The next one's going to be, well, this 2 divided by 4 is going to be 1 over 2. And this is going to be cotangent x and 1 less power, so x to the 2. X divided by 2, like that. And notice here, this cancels with this. Just notice that. And the next one here, because we're going to get a what it's called a telescoping sum. The next one is, we're going to replace this tan x over 8. So, and then divide by 2. We're going to replace it with this identity over here. And then, divided by 8, yeah. So we're going to divide all that by 8. So we're going to get a cotangent x over 8 divided by 8 minus, and there's always that extra 2 there. So minus 4, yeah, so divided by 4. Cotangent x over 4. So notice that these always match. This divided by 1 there matches the power. So you have this 4, 4, 2, 2, and there's 8, 8, 4, 4. They always match. And notice also this cancels with this, and this pattern keeps going on and on. The next one will have a cotangent x, a minus a cotangent x over 8 divided by 8, and those will cancel, and so on. Plus, and keeps going dot, 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 plus, and then all the way to the end. And you can see the pattern. The next one's going to be cotangent x over n, or actually a 2n. Divide this by 2 to the n, because this one's 2 to the 1, 2 to the 0. This is 2 to the 2, 2 to the 1. This is 2 to the 3, 2 to the 2. And then minus, and the powers are the same there, and then minus cotangent of x over 2n minus 1 over 2 to the n minus 1. And then this would cancel out. So notice how always the right side cancels out. All you're left with then is this and this. And I'll cancel this out too. So this equals to negative cotangent of x plus cotangent of x over 2n over 2 to the n. And I'll just put an arrow, put this Sn, and I'll just box this out for now. So that is our nth partial sum. And recall now that the above cancellations, this is known as the telescoping sum, and I've gone over that in several videos before. So let's go further. Now we have to take the limit of the partial sum to infinity to get the exact sum. Yeah, the exact sum of the series. So yeah, again, it's taking the limit to infinity. so that s is the sum equals to limit as n approaches infinity of Sn. And now this equals to, well, this cotangent of x, there's no n there, so we just take it out of the limit, the cotangent of x plus limit as n approaches infinity of cotangent x over 2n over 2 to the n. Alright, so now that we have this right here, and now just recall the trig identity, or just the definition of cotangent. So recall that cotangent theta is equal to 1 over tan theta by definition, and then the tan theta is equal it's also equal to pretty much by definition sine over cosine theta. It's actually not definition, but it's pretty close to the definition. Just an identity there, sine over cosine theta. So that's what tan, but then it's upside down. So sine over cosine, but then you're going to flip it over. So cosine theta over sine theta equals to cotangent, like that. So we're going to throw that inside that limit. So let's just take a look at that limit separately. Thus, limit as, so let's write this right here, limit as n approaches infinity of cotangent x over 2n becomes like this. I'll write this as a giant fraction, so there's a 2n there, and then the cotangent becomes cosine of x over 2n divided by sine of x over 2n, like that. And note that x over 2n, this approaches, well, you have x over 2 to the infinity approaches x over infinity approaches 0. So both sides we have a 0, but then what we get is a cosine 0 over, this is going to be, well, 2 to the n is infinity, times it by sine of 0, like that. And if you recall, cosine 0 is 1, and this is, so it's approaching infinity, and then sine of 0, sine of 0 is 0 times 0. So this is indeterminate, and I'll illustrate that in a bit. And I'll just write this down, indeterminate, because you have an infinity, times it by is 0, so you're not sure if it cancels or diverges. Indeterminate. And here, just recall the trig functions of cosine and sine. So recall. So if we have it like this, if this is our let's put theta. So recall that the sine looks like this, etc. So that is sine. Now let's put this. This is at 1, and this is at 0, like that. This is our sine. So it's a 0 is over there. It's just sine theta. And then the cosine is just the opposite of that. So it's going to be start at 1, goes to 0 there, goes to the peak here, goes to 0, etc., goes to the peak there. I'm just going to draw this side only. And we might as well keep going. So this is at the peak, it's over at the 0, and so on, goes over here. This is the cosine, like that. And this is our cosine theta. Notice how it's at 1 here. So at 0, it's at 1, and so on. Alright, so let's continue further. So let's try to solve that. Yeah, we'll try to solve this here by trying. I'm going to multiply, the solutions manual did this, multiply the top and bottom by x. So try, let's go over here. So let's write that limit. Limit as n approaches infinity of cosine x over 2n. Yeah, over 2 to the power of n. This is times by sine x over 2n. So multiply top and bottom by x. And then I'm going to separate these two just to get the infinity one by itself, so or separate with these 0 there. So notice as infinity, if we get it on top, so it'll be a 0 and then divided by 0. Or an infinity over infinity. Just to do that, so then we could apply L'Hopital's rule. So this right here, combine these together. This just equals to limit as n approaches infinity. I'm going to write this x with this cosine. Cosine x over 2n over x. Yeah, times it by, and this x, I'm going to combine it with this x over n, 2n. So the same thing as writing x over 2n like that, over sine x over 2n like this. Like that. Because yeah, this is x divided by 2n, same thing as writing divided by 2n over here. So we just write it like this. And now this one here, this x, we could just take it out of there. And also we know that this limit right here goes to 1. This part here, because we have this goes to 0. Cosine 0 is just approaching 1. So that means we could just take that out. So this equals 2, just using our limit rules. This equals 2, so it equals to 1. And then this x, we could just take it out anyways because it doesn't have the n value variable there. So it's not part of the limit. So this just equals to 1 over x times by limit. So the only one that matters is over here. X over 2n over sine of x over 2n, like that. And now what we'll have is, remember this is infinity there, so 1 over infinity is approaching 0. And this one here is just approaching 0. So it's approaching 0 like this. Yeah, this is number sine 0. It's approaching 0 there, or just equals 0. So what we have that is a 0 over 0, and this is also indeterminate, but we could write this in L'Hopital. We can solve this using L'Hopital's rule. Indeterminate again. Yeah, so whenever we have indeterminate such as this infinity times 0, we want to make it such that it's 0 over 0 or infinity, and then we could use L'Hopital's rule, and I'm going to denote that by putting h on top of this equal sign. So that means we're taking the derivative of the top and bottom. So limit, and then take the derivative of this, and just for completeness for this time, but later I'm just going to do it automatically, d over dx, x over 2n. And then, yeah, just divide this all out by sine x over 2n, like that. I mean, d over dx of this. D over dx of this. Yeah, just move that over, put a bracket, etc. And this equals to 1 over x times by limit as the derivative of x over 2n. 2n just a constant, so let's put a 1. So 1 over 2 to the n. And then the bottom part right here, I'll just move this limit higher up. And recall the derivative of sine is just going to be cosine. So this is equal to cosine of x over 2n. And then using chain rule, we have to multiply by the derivative of the inside. That's just going to be 1 over 2 to the n. In other words, this cancels. This whole thing cancels with the top. This cancels. This cancels. So what we're left with is, well, this cosine 0 is approaching 1. So that whole thing, the derivative is going to be this whole limit as n approaches infinity. Yeah, let's put the limit again. I think I missed every single one. Whoops, yeah, n, not pi. Looks like a pi. Like that. And yeah, so just do that. Then this equals to, well, 1 over x times by 1 over 1 equals 1 over x. And note that this is for, well, when we have the scenario where x is not equal to 0. Otherwise, you're going to have 1 divided by 0 goes to infinity. So yes, so you can't divide by 0 there. So note that I used the L'Hopital's rule in the above limit here. Take the derivative. And here's a reference from my earlier video. I'll bold this. So L'Hopital's rule, suppose f and g are differentiable and g prime of x is not equal to 0 on an open interval I that contains a except possibly at a. Suppose that you have limit as x approaches a of f of x equals to 0, and for g of x goes to 0, or you have one going to plus or minus infinity, other one's going to plus or minus infinity. In other words, we have indeterminate form of 0 over 0 or infinity. Then the limit is equal to the limit of the derivatives of f prime of x divided by g prime of x. So this one, f limit as x approaches a of f of x divided by g of x is equal to the same but with the derivatives. And yeah, it's equal to it if the limit on the right side exists or is infinity or negative infinity and so on. Yeah, so thus putting this all together, we have for x is not equal to 0 or x is not equal to k times pi, and I'll get to that in a bit, where k is any integer, and then combine this together. So our s here is equal to limit as n approaches infinity of Sn. And before we even get to that, yeah, this equals to this, a negative cotangent x plus, and then this whole thing becomes 1 over x. but also let's write the limit initially. So let's write the series right here. So sum of the series, summation from n equals 1 to infinity of 1 over 2n times tan x over 2n. So let's write this all out. So that's what we have is our sum is equal to, or our s is equal to the sum, is equal to summation up to infinity of n equals 1, and then 1 over 2 to the power of n times tan x over 2 to the n. And this equals 2, or actually we don't need to write s there, just write, this is, the summation is, or s, equals to the limit as the partial sum, as n goes to infinity of the partial sum, like this Sn, and this equals 2. Just put it all for completeness, just a solution manual just puts it all together. Limit as n approaches infinity of negative cotangent of x plus our 1 over 2n cotangent of x over 2n. If you scroll up, that's just this part right here. So limit as n approaches infinity of Sn. So we have this negative cotangent of x plus this right there, and this all equals to, all equals to, just move it over to this side, equals to negative cotangent of x plus 1 over x, like that. And I'll just box this in. So that is our limit, or that's our sum of the series. Alright, so that's what we have there. And also, the reason we have this x not equal to k pi, so first we all know this one, x is not equal to 0, because if you plug in 1 divided by 0 there, it goes to infinity. But if you have this x is not equal to k pi, if x equals to k times pi, where k is any integer, recall, let's put here, recall that, well, cotangent of x, so notice that there's a cotangent there, cotangent of x is equal to 1 over tan of x. And if you graph out the tan of x, it looks like this. This is our x, this is our tan of x, and recall what the graph looks like from my earlier videos, went over it. This is at pi over 2. This goes to pi over, negative pi over 2. So this one here, 1 over, whenever it's 0, here's at 0. Then the next one is, it's going to look something like this. And it's going to keep going. And this is, again, at 0. And this distance right here, this is pi over 2. This is going to be pi. And it keeps going on, and so on. So then this distance is going to be our pi. So at pi, or at 2 pi, etc., 3 pi, and so on. So thus, this equals to 1 over 0 is goes to infinity at, or here, just move it over here. So this, make it make room over, make room for it over here. So cotangent of x equals 1 over tan of x. This equals to a 1 over 0, which goes to infinity for x is equal to k, any integer times pi. So any integer times pi is always going to go to 0. It's 1 over 0. So we can't have that. Also note, for x equals 0, so instead of having to write it over here, if x equals to 0, so right here, if x equals to 0, we don't even need to do the limits or anything. We could go straight to, so if x equals 0, then summation, we could just solve the sum right away. N approach infinity, or I mean n equals to 1. So n equals to 1 right here. So n equals to 1. And let's just write our summation, 1 over 2n. 1 over 2n times tan of x over 2n. This just equals to, well, tan of 0 is just 0. And then this one, whatever these are, it doesn't really matter. Because every single term is going to be 0. So you're going to have a 0 plus a 0 plus a 0, etc. And so then plus dot dot dot. And any finite n value, it's always going to be, well, 0. Divided by, even if it's a super large number, you're still multiplying by 0. And this equals to 0. So it's not, because the thing is, the difference is it's not a limit that this is going to 0. This equals to 0. So this whole thing equals to 0 when x equals 0. So we don't need to even do this equation, because we can't do it for x equals 0 there. So yes, that is for that question.